Okay, so a couple of announcements. Firstly, so Wednesday lecture, two of my student, my postdoc. So they'll cover two topics. Number one, Android, so Android architecture and app development. So some of you who are doing projects around it, it could be useful. But generally speaking, that's an example. I guess an embedded OS. And then also one of my postdoc, Wen Tao Wang, what he will do is spend around 20 minutes or so to go through how you take sensor data, learn a model over it using machine learning tool so that you can then make use of it to make some inferences. So many of the projects kind of need that, like detecting occupancy or whatever, how much stuff is in a spoon. Some of these projects which are there, they all boil down to taking sensor data, coming up with some features, and then learning a model on it. There are plenty of models like which either kind of give you a yes/no answer, classify it into one of various categories, or estimate some numerical value. So Ventao is going to basically walk you through using one of the tools out there how that process works. There are many machine learning tools out there. One could use anything, but he'll just walk you through one just to kind of expose to you what the process is. That's something which sort of machine learning classes cover much more in depth. So here it would be just giving you a sort of a user's perspective on it. It's fairly easy because you don't need to know how kind of a tool under the hood kind of the techniques are, but from a purely utilitarian perspective, how you can use them in your projects. The other part, so Wednesday is going to be devoted to that. That lecture will not be recorded because there's going to be a lot of demos and kind of live code and all. So if you miss it, you'll miss it. There is not going to be a recording for that. If you already know how to do Android app development and are comfortable ML, you can, I guess, skip it. The second thing is around half an hour ago, I sent out a form, Google form, with asked you for project information. Make sure to fill that out. It's due tomorrow morning. I think at this stage, I think everyone has spoken with me, but this form asks you for specific uh, things. And then the other thing you have to do is you have to create kind of like a little website for your project where you can keep depositing material, kind of your continuously updated project report. What I would suggest is just use Google Sites. It's very easy to create a page out there and then just put the link to it. But you can use anything else. It could even be like a Dropbox folder where you have created a website or your own web server or whatever. I don't care, but a precise mechanism. But just provide a URL which you can update. But I found Google Doc to be kind of a good way of organizing it. Okay, so and the final thing is homework. I'm still kind of working on it, so I'm going to be handing out hopefully later today. So we'll have a programming homework and a conceptual homework. So there are two things going out. Okay, so the topic that will start today is scheduling. So we saw past couple of lectures how software gets organized in embedded system, and one of the things that emerged was that you need to schedule multiple things on a single processor. Now, this is something that general purpose operating systems, of course, also do, but as we discussed last time a little bit, they don't have timing constraints. So the key thing out here is that how can you schedule while meeting timing constraints? And around that, a whole bunch of theories and all have emerged, and they find their application in variety of scenarios. It could be scheduling of a CPU, it could be scheduling of a wireless link, it could be scheduling of an internet router. All of them fundamentally are about, I have a resource, it needs to be shared among multiple parties, and I have some performance constraint. That performance constraint could be one of throughput, that I need to be able to sustain some data rate, or it could be one of latency. For embedded systems, it's latency that matters more. What I mean by that is some request has come, and there are many other requests here. Some request has come, and I need to make sure that it is met within a certain deadline. And probably the second constraint which comes from scheduling is, and which we also saw a little bit of, about power, that we want to do it in a way that minimizes energy consumption. This slide set is going to focus only on timing. So but towards the end, I'll kind of talk a little bit about power. Probably the most grand theory in this space is something called rate monotonic theory. So this slide set basically walks through that. And then next slide set will cover just some more advanced techniques that exist. For this lecture, actually, since it is a little bit more formalized material, so I've sort of indicated two papers, which essentially are kind of the seminal papers that describe the modern state of rate monotonic scheduling. So, operating system. So, in a typical embedded system, you are going to have a whole bunch of actuators, sensors, processor, whatnot. And from a processor's perspective, so just restrict ourselves to a single processor and a bunch of these things. So I have a bunch of tasks, and then I have to kind of do different kind of things like read a sensor reading, write something, command to a motor, transmit a packet, receive the packet, all of these things. And oftentimes these systems, when an event happens, I have to do it in a timely fashion. So you'll have constraints on rate, like for example, a sensor must be read at a particular rate, or motor must be commanded at a particular rate, and you may have constraints on latency. That is, from the point a sample gets ready, you have to read it within a certain time. So very trivially, for example, let's say I have a microphone being sampled at 44 kilohertz by the A to D converter. A sample comes, and then a trivial deadline is, because usually there is a single buffer, before the next sample is done, I have to read the current sample, right? Now, if I had a longer queue, I may have a more relaxed requirement, but ultimately there will be some requirement. And this is so even though I may be meeting just a period requirement, there would be a corresponding latency requirement nevertheless. So we will formalize this. Main thing that an operating system has to do is then take these tasks, schedule them at the right time, enforce this. So whenever we schedule, there is a implied contract. Like a task may say, I need so much computation time. What if the task violates it? Or for example, a task may declare it needs some resources, and what if the task violates it? And then final thing is it has to optimize for something like power would be an example. It's some other metric. So I have to make sure that I meet the deadlines. I need to make sure that I do not let tasks violate the promises they make, and I need to make sure that I optimize some resources. So that's what OSs do. In real time versus non-real time, the differences come out as the following. So if you look at, like, let's say you're designing a web scheduler for a web server or desktop machine and all, what you really care about are things like throughput or interactive performance, things like that. With real-time systems, the main thing is, can I schedule while meeting the timing constraints? That's kind of part of it. You're looking at it from a different perspective. Responsiveness in non-real-time systems, fast average response time. Okay, we don't care about whether each and every mouse click gets specific response time, but we do expect our laptop to be responsive. Whereas here, we have to make sure that in the worst case, some timing requirement is met. So again, change mindset. And final thing is, what happens under overload condition? Let's say, for example, there is some unanticipated task came in, maybe too many interrupts are coming, or things like that. In non-real-time system, you would kind of usual goal is, let everyone be penalized more fairly. Okay, so if the processor slows down, everyone kind of takes it. Here, some tasks may be more crucial to stability and some less so. So there would be some things which are more critical for our system not crashing or kind of not doing something which is which causes some sort of a damage. So that's real time from a very high level perspective. Now, how we organize these things under the hood is, so there's a concept of tasks. So you can think of tasks are something which issue a sequence of requests. Okay, so for example, it could be a task which reads measurements from a sensor. So every time there is a data ready on the sensor, this task is going to read it, process it, perhaps ship it someplace. So there's a sequence of requests, and each one of these requests is called a job. Okay, so task refers to the sequence, job, or I often in my slides call it instance of a task. So that refers to a specific instance of the task that arrived. Okay, so in my example of the sensor, there's a sensor reading task, and every time the interrupt indicates that there is a sample to read, a new copy of this task essentially runs, or whatever this task has to run, handle that. So that's called the instance of the task or a job. So associated with jobs, so that's our now unit of work. Each task has a sequence of jobs. This unit of work would have some requirements on it. It would have some computation time requirements and maybe perhaps other resources. Like for example, it may say, I need some time on the network. I need to do some I/O. It may have some resource requirements. So task is a sequence. Job is each instance of that task. And from a time perspective, a particular request of the task will be released at some point in time. So I should really say job release out here. But at some point in time, the task is released, an instance of the task is released. And then I'll have a deadline requirement that is from the point it was released. At some point in future, I must finish the work. Okay, and to finish that work, I would need all the stuff that was required out here. I'll need some amount of computation. I may need some other resources, and from a scheduling perspective, I have to make sure that this particular instance of the task gets those resources so that it is able to run. It may happen that I can run it immediately, or it may be that it's somewhere later. Here I show that it runs contiguously. It may not even be contiguous. It may be that part of it runs, then I give the CPU to something else, then the remaining part runs, so it could be fragmented. That's what we called as preemption kind of approaches. But point being that I need to be able to finish the amount of work needed by this job before the deadline comes. Okay, so very simply stated. And the main thing is, for us to be successful, I need to be able to make this promise for every job of every task. Okay, that's kind of the constraint. Now, to begin to simplify this more, yeah, go ahead.
I'm just going to ask, is this specific to a real-time system, or is it all?
It is specific to real-time systems. The thing is, most embedded systems will have some real-time component, because since they interact with sensors and actuators, and the best way we design sensors and actuators is with some sort of a timing constraint. So there'll always be some part of it. Okay. Yeah, so good question. I guess the thing is, many embedded operating systems do not provide real-time support. Okay, so in that case, what you end up doing is you kind of deal with this thing at the lowest level manually. Okay, so the scheduler may not give any promises about deadlines, but then you will make sure. And the one way of making sure is, if you have to meet timing constraint, is disable it in other interrupts at the time, so that nothing else can interfere with you. But so as long as you have a few things, it will work. That's one approach. The other approach is just use things which are really fast, right? I mean, if I'm handling something at whatever every 1 millisecond, and I'm running on a 10 gigahertz processor, most likely kind of things will work out. The problem which comes is, since we are also resource constrained, power and stuff like that, as well as cost constrained in many cases. So you do not necessarily have the luxury of just throwing hardware at it. That's one problem. The other is, actually, ironically, it turns out that in many cases, if you make the hardware faster, you may actually miss deadlines, which you will not otherwise. So things can get counterintuitive, particularly if you are in a multi-core kind of setting and all. So that approach is fraught with problems, but we often, people often do it, right? So we, take our laptops and all. They handle media perfectly fine. And the reason they do it is they are insanely fast relative to kind of the rate at which audio is sampled and all. Another thing is, a lot of stuff gets done at the lower level chips. So our laptops or smartphones, for example, Android handles audio and handles video, but the bulk of the real-time work is actually being done by some signal processor sitting deeper inside. Okay, and that's where the real-time stuff takes place. And then once all that stuff is done, at the final OS level, you can basically say, I'm fast enough, things will sort of work out fine. Okay, so hopefully that clarifies things. Okay, so what's the model of the task? So the most common model which is used is one of a periodic task. Okay, there is also asynchronously arriving tasks which are kind of patched onto it. But the most common model you'll see in real-time literature is that I have a task which is periodic. What that means is that the different jobs in that task are going to arrive in a periodic way. Okay, so that period is this T sub I. Okay, so every T sub I indicates the ith task. Every T sub I, a new request of that task will arrive. That C sub I refers to the execution time. And since we care about things working out, always working out, so usually this is specified only in terms of a worst case execution time. Okay, so CI refers to worst case execution time. You will often see it referred to as WCET, okay, worst case execution time. In some other cases, you may be given best case execution time, you may be given a distribution, all sort of things. So the simplest model is worst case execution time, the period, and the final thing is completion deadline. That is, how much time after a job arrived does it need to finish? So if a job arrives at time t, then it will have to finish by time t plus t sub I. Most common model, again, that you'll find is where d sub I is the same as t sub I, which is another way of saying that I need to finish the current request before the next request arrives. Okay. What I don't know in this model is when did the first copy arrive? Okay, so system started. At some point, I started using the sensor and the samples start coming. I don't know what absolute time the first request arrived. So I cannot say, so even though I know the period, I cannot say that in terms of my watch at what times the tasks are arriving. I can say it once I have seen the first instance of it. Okay, when the first job arrived, after that it is every T sub I. But when I'm designing the system, I don't know that. I don't know whether first copy of all my tasks are going to come at the same time. Will they come at different times? How much time after power up will the first one come? None of those things I know. So, so if you think of like that initial offset, that is after system power up, when the first instance of the ith task came, it's kind of like the phase of that task. Then I don't know the phases. Okay, but they do come periodically. That's the only part I know. So in this example, I have two tasks. Task 1 is coming every 4 time units, so its period is T sub I. Looking at it, you can also see it always takes time 1 unit. So this task is Ci equal to 1, Ti equal to 4. Okay, and deadline, very common model is, like I said, that deadline is equal to T sub I. Okay, so oftentimes we just kind of ignore it. For now, we are going to assume that deadline is equal to T sub I, then we will relax it and say, okay, what if deadline is less than period? And in the final case is if deadline is more than the period. What do you think will happen if deadline is more than the period? What does that mean for my system? Good, 2 or more, right? I mean, so I may have sensor samples arriving every second, but I may tell you that you have, for every sample, you have up to a minute to handle it. That means that I can actually keep 60 samples somewhere in the processing, right? So it kind of suggests a pipeline type system, basically. Usually not done, but many systems have that kind of requirement. I mean, if you think about it, let's take audio, voice over IP or some sort of audio application. Audio is sampled at kilohertz, tens of kilohertz, so that's in millisecond, fraction of a millisecond. Whereas, let's say you're designing a cell phone for bidirectional human conversation, up to half a second of latency is acceptable. Okay, that is, we converse fine if the system had that much delay. Cell phones tend to have a lot more delay and all. So what that means is that there's an insane degree of pipelining which goes on in our acoustic systems. In other cases, that may not be the case. A challenge which often comes is that applications have an overall delay budget. So I have a sensor gets sampled, processed, sent over the network, received, some other thing happens, and And the overall deadline that I have is the end-to-end deadline. From the time the sensor was collected to the point a decision was made. Let's say, for example, I'm designing a mHealth system. I have some ECG sensor on me. ECG is sampled at kilohertz rates. So it's working at kilohertz rate. Then it's sent over some Bluetooth link to my phone. On my phone, some detection happens. Then it's sent over, let's say, the cellular link to some backend server. And there, if it realizes something, maybe a notification has to go out to some sort of emergency care center. And probably there will be an overall deadline on that for it to be medically acceptable. How much of that deadline I have in each one of the stage is a very hard problem because you can divvy it up many different ways. At the lowest level, at the sensor sampling level, the usual model is we will say, let's keep up with the sensor sample rate. That is, one sample, make sure that I have read it before the next one comes so that I don't have to do a lot of buffering. So task 2, what is the period? Well, as we can kind of see from it, it appears to be arriving every 4 time units, but it's not being executed in a periodic fashion, as you can see. Okay, so what's happening is this. It's always, as you can see, okay, it's always kind of deferring to task 1. You could see it out here that it was released at time 15, so it was released as it's coming every 5. So it was released at 0. Next copy was released at 5, then 10, then 15. And see how this 15 was. So at 15, it started running, but then a copy of task 1 came. So scheduler decided to give the CPU to that. So this is what we call as preemption. And then once this copy of task 1 was done, we again started running task 2. So in this case, I have a scheduler which is giving priority to task 1. A very important metric associated with this, with any task set is what is its processor utilization factor, or sometimes you will see it as called as utility. And that refers to what fraction of the CPU is needed collectively by these tasks. So if I look at a task with computation times Ci and period Ti, that means every time Ti, it needs CPU times C sub I. So that basically means it needs C sub I over T sub I fraction of the CPU, right? If none of the other constraints were there, for me to just run the task, I need this amount of the CPU. And then you can talk about what is a total processor utilization. Total processor utilization in this case, so this task is coming every 4 time units, needs time 1, and this task is coming every 5 time units and need times 2. So first one's utilization is 1 over 4, second one is 2 over 5, you add it up, it's 0.65. This number is actually a pretty important number because firstly, what can we say about it? So what can you say about task, if I give you a group of tasks for them to work?
How much I use the processor, how much is busy.
How much is busy versus idle, something. But what about, like, if I give you a task set where processor utilization factor total is more than 1? It's not schedulable, right? So right there, what if I give you you have a task set, a processor, now I give you a faster processor. What will happen to processor utilization factor? It will go down, right? Let's say I do some compiler trick and all, and a task takes less execution time, fewer instructions. Again, the utilization will go down, right? And a lower utilization means that I can either switch to a slower and cheaper processor, or maybe I can shut down the processor and save power. So lower utilization is good. Or another way of saying is that lower the utilization, the more the headroom I have, okay, and therefore I can kind of get away with save on money or joules or whatever.
So if you have more than 1 core, you can go above 1.
Sure. If I have more than 1 core, I could go above 1, but you will start entering into this issue. Can I divvy up the tasks? Okay, and that's a separate thing. But you're right. So more precisely, then the ceiling of this indicates the minimum number of CPUs that you need.
Excuse me, about this tool, is there any constraint about the relation between deadline and value when applying this rule, as if the deadline is more than?
Oh, when applying this rule, see, all this is saying is that this fraction of the time the CPU will be busy, just because processor utilization is less than 1 overall, does not mean that I can meet the deadlines. In fact, you will see that there are cases where you cannot, depending upon the type of scheduling scheme you pick. We'll see those results very shortly. Okay, so now it boils down to the scheduler. Okay, some scheduler, there are schedulers which, under some conditions, can schedule any task, any set of tasks which have utilization up to 1. There are other schedulers which cannot, which have a lower limit. Okay, so that depends upon the scheduling algorithm. Okay, so processor utilization factor basically says that what fraction of that, if I am able to schedule that task set, what fraction of the time processor would be kept busy. Okay, and so for n tasks, I can kind of define it this way. And if u is equal to 1, that means processor is fully utilized. If it's u equal to 1 and I'm able to schedule the task to meet the deadlines, then processor is fully utilized. Okay, if it is more than 1, I better look for a faster processor or more processors. And if it is less than 1, then maybe, depending upon the scheduler, I may be able to get away with a slower processor. Now, with these things put together a little bit more formally, so you can say that Ti represents inter-arrival time, which we are calling as periods, and simplest models we are saying Ti is constant, that is, things are periodic. Runtime, we are saying we'll assume that everyone takes the same runtime, or in a sense, everyone that every job of a given task takes a corresponding worst case execution time. Deadline, we are basically saying that each task must finish before the next request. So deadline could be equal to T or less than T. We're going to not worry about the case where deadline is more than T, so no buffering. Tasks are independent, they don't interact. Okay, so if it will never be the case that somewhere in the middle of the task it needs to talk to one of the other tasks. Okay, so we rule out that part. We'll see later on. This is probably the strongest assumption we are making for now, and it causes lots of problems, but there are ways of dealing with this thing. There are other things like that we are assuming all tasks are fully preemptible. That is, a task can be stopped anywhere and restarted again from that. In a theoretical sense, even in the middle of an instruction. Okay, of course, even a perfectly preemptible system can only do things at the boundary of an instruction, at the clock cycle boundary. We'll also assume all OS overheads are 0. So if I switch from one task to another, it doesn't cost me anything. And we'll also assume a task cannot suspend itself. Okay, so that kind of relates to the tasks are independent; they don't need anything else. Okay, once a job arrives, it is ready to run. Okay, and so if I give the CPU, it will run. Okay, there is nothing else that it needs. Okay, so then now you can imagine. Question? Yeah.
How do you measure the worst case execution
Excellent
time?
question. I think a similar question a couple of lectures ago also. How do I know how much time a function will program take? Very hard task, generally. In fact, generally speaking, in software, can you even tell whether a program will stop? No, it's actually a halting problem. It's an undecidable problem. There is no algorithm which can even tell you whether there's no algorithm that can take a program and tell you whether it will stop. Okay, so that's out of the window. Now, having said that, most of the real code is not arbitrary, right? I mean, so what you do is you trace through all possible paths through the code. Okay, so let's imagine I have a code which reads some sensor data. If sensor data is something, does something, so you kind of trace through these things. Very much like if you're designing a digital circuit, you kind of trace through different paths and identify the critical paths. You kind of do the same thing out here. So there are software which can take programs which they pose constraints on it because we don't want to enter into the halting problem kind of situation. So let's say, for example, if I prohibit loops, if the only thing I have is if then else switch statements and all, as you can imagine, I can enumerate every way the program can start and end. Okay, and then I can count how many instructions would be there. It will be a hard job because I may still have data dependencies and all, but they can all be kind of systematically resolve, and you can come up with the worst case. So that's one approach. The other approach is a very pragmatic one. You take the program, feed a lot of random data at it, you'll get a distribution, take the worst case. Okay. So both these things exist. There are, in fact, the very same companies that make tools for designing VLSI, Synopsys, Cadence, these kind of companies, graphics, who kind of create tools, they also create like similar tools for embedded software. So you can take pieces of code, it'll tell you how many clock cycles it will take for simple kind of processors. Now there are complications there also. Processors have caches. So if the cache is full or not, it may take different amount of time. These complications come into play, but again, for at least simpler processors and some constrained code, you can answer these questions. Generally speaking, it's an undecidable problem, so no answer to it. Okay, so these are assumptions. So now, in essence, what we have is I have a set of independent tasks, tau 1 through tau n. They have some period, or another way of saying is that they have a rate at which ith task is being requested. We are assuming that we don't know the phases. We don't know when the first job of the ith task came, okay, which is why I only know the period. If I knew this, then the implication of that is that forever I knew precisely when the tasks are coming, the jobs are coming, okay, and I can do a static scheduling because I know it up front. I can kind of design a static schedule, but I don't. If I knew them, the task set is called a concrete task set. If I don't know them, then it is called a non-concrete task set. So non-concrete means that I have to be prepared, my scheduler has to be prepared that any values of the phases may occur. Okay, it could be that the first copy of all the tasks come at the same time, right at the boot up time, or it could be they arrive in a staggered fashion. Okay, so I have to make sure that all of them, that if I say, if I tell the programmer, okay, this set of tasks with those properties TCD are acceptable, then I'm basically saying they will work for any arbitrary value of R. Okay, and usually that's the more common model. It's very hard to predict what the R's are going to be. Okay, in some systems maybe, but usually not. Run times are the worst case execution time, and again we are assuming this sort of t sub I is less than t sub I, less than equal to, and very common model is they are actually equal. So scheduling algorithm. So scheduling algorithm is now faced with such a set of tasks. It basically has to decide, give you a rule, how to run this thing. Now the rules can range from static to dynamic. Okay. One possibility, and it's probably the one which almost all real-time operating systems adopt. Okay, most common one is the so-called preemptive priority-driven scheduler. Okay. Now what does that mean? It means that tasks are assigned priorities. These priorities could be assigned statically or dynamically. That is, it could be that upfront I'm given the code, compile time, I analyze this thing, or whatever, start time, I analyze it, and I say this task number 1 has the highest priority, task number 2 has the lowest, task 3 has the intermediate priority. I just assign the priorities and then keep it fixed. Or the other alternative is that I don't give them any priorities, rather the OS does it at runtime, and it can keep shuffling it, okay, it can keep changing the relative priority. In this course, normally when I talk about priority, I would say priority 1 means highest priority, priority 2 is next lower, and so on and so forth. But these are just arbitrary number. All you need is an ordering among them. We'll also assume that if two tasks happen to have the same priority, as far as we are concerned, they are equal to us. Okay, or better yet, we'll just assume that we'll break the tie. So no two tasks have the same priority. At any instance, so all the OS now promises to do is that given the priorities, and if it is assigning the priority dynamically, it does so, at any instance, the highest priority task is running. So what that means is that if something happens to my system, which results in a new job arriving, or an existing job becoming ready to run, then and this job is higher than the current, has a priority higher than the currently running one, then we will stop the currently running job and give the CPU to this newly activated, newly ready job. So for example, it could be that I have two sensors. One sensor is higher priority. but I'm currently running the lower priority. The lower priority data arrived. I was processing it, and in the middle of that, the higher priority sensor sample became available. Interrupt handler fired. That interrupt handler will tell the OS, "Hey, I'm ready." The OS at that stage will say, "Oh, okay, you have the higher priority." It will give the CPU to that. It will stop the currently running task. So that's the promise they're making. So if you so within this framework, different scheduling algorithms basically boil down to different ways of assigning the priorities, right? Because otherwise the strategy is the same. All I'm promising is that we'll run the highest priority task. So the only way scheduling algorithms differ is how they assign the priorities. And presumably they assign the priorities by looking at those three parameters, C, D, and T, okay? Or in the simpler case, just C and T. And they could either assign these priorities upfront and fix it for the life of for the runtime, or alternatively, maybe I have algorithms which keep changing the priority based upon some systematically defined strategy. So why do priorities matter? So let's take a simple example. I'll just show that under one condition things will work, and with a different priority they won't. So let's imagine I have two tasks. Task 1 has a period of 50 milliseconds and a worst case execution time of 25 milliseconds. Task 2 has a period of 100 milliseconds and a worst case execution time of 40 milliseconds. And deadlines we assume to be equal to the period. If we add up, if we find the processor utilization, we will see that task 1 has a processor utilization of 25 over 50, that's 50%. Task 2 has it 40 over 100, which is 40%. You add them up, total requested processor time is 90%. And the question is the CPU fast enough to be able to schedule it? And since there are two tasks and we are operating in a priority-driven framework with statically assigned priorities, then there are two choices. Task 1 is higher or task 2 is higher. If I look at task 1 is higher, case 1, priority of task 1 is higher than priority of task 2. If we kind of just look at the timeline, kind of like a simulation of this, what is happening, and let's start by assuming that the first, both the tasks, a job for each one of the two tasks arrived at time 0. Since task 1 is higher priority, it will run and it will take time 25, its execution time. Once it is finished and the next job of task 1 has not yet arrived, so now the CPU can be given to task number 2, so it will start running. So task 1 finished at time 25, obviously met its deadline. It arrived at 0, finished at 25. I'm sure you can kind of reason here that since task 1 is the higher priority, whenever it arrives, it will get the CPU. And since it needs time 25, it will always meet its deadline. Okay, so that's what's happening. Next copy of task 1 came at time 50, it will finish at 75. The next one will come 100, will finish at 125. Task 2 is the one which takes the hit. So now task 2 starts running. The first copy of task 2 arrived at time 0, started running at time 25. And it needs time 40. So it will run from 25 to 50. But then at 50, another copy of task 1 came. So task 2 is preempted midway through, right? It has finished 25 out of 40. Now from 50 to 75, task 1 will run. At 75, I will give the CPU back to task 2. And now it needs 15 more units of time. It will get it because, okay. And then here the CPU is lying idle. Okay, and you can imagine at time 100, I will have a new copy of each one of the tasks arriving. So it's as if the whole cycle will repeat after that. So based upon this kind of a simulation, we can at least convince ourselves that this system is schedulable. Agreed? Let's look at the other way around. Now, this time around, task 2 is given the higher priority. A copy of each one of them arrived at time 0, but task 2 has a higher priority, so it gets the CPU. And it will hog the CPU until time 40. At time 40, task 1 gets the job of task 1, which came at equal to 0, will get the CPU. And it will need 25 units of CPU time, but it will miss its deadline at equal to 50. Okay, so in this case, we can see that priority ordering does matter, right? If I gave higher priority to task 2, system doesn't work, even though processor utilization is still 90%. Okay, so processor utilization is an insufficient indicator of schedulability. Okay, you have the scheduling matters, or in our framework, the priorities matter. So is this point clear, right? So which order I assign priority at least mattered out. Now, looking at this, what can you say? Like I gave priority 1, task 1 the higher priority. It happens to have a shorter period, shorter deadline, so it's coming more frequently. Okay, so that's kind of the intuition, and rate monotonic kind of also that rate matters. Okay, so rate monotonic scheduling is so firstly, rate monotonic scheduling is for the case where deadline equal to period. Okay, so we are only looking at that. Rate monotonic scheduling strategy basically says that assign priorities according to the rate, according to inverse of t. Okay, independent of runtime. So it doesn't matter what C's are. Okay, of course C over T has to meet some constraints, in the sense obviously has to be less than equal to 1, but my priority assignment will be solely based upon the rate. So if there are 2 tasks and one has a higher period, it will have a lower priority. Okay. There's a generalization of this which says deadline monotonic. Okay, which says if D is not equal to T, D is less than equal to T, then I'm going to assign them monotonic with the deadlines. And again, there are no known results for D greater than T, so we're going to ignore that. So D less than equal to T, you can basically, I think the more general term to use is deadline monotonic. I'm going to assign priorities. The tighter the deadline, the higher the priority. And intuitively, of course, I mean, there's some appeal to it, but there is a very strong result for rate monotonic priority. It says that if rate monotonic priority assignment cannot schedule a system, then there is no other way of assigning the priorities in a fixed way, statically, that will ever work. So if I give you a task set and I task set with the appropriate characteristics, so T equal to D, and I'm given the CIs, and you have to find the priorities, then and you don't know whether it's schedulable or not, then the first thing you are going to do is you are going to say, okay, let me give the priorities in a rate monotonic way and check. We haven't talked about how to check, but let's check. And if the system is not schedulable, then nothing else can schedule it. If the system is schedulable, then rate monotonic obviously works, but maybe there are other ways of assigning priorities that could also work. They may be better in some regard, maybe they'll consume less energy or whatnot, but they may also work. So rate monotonic is universal in this regard. That is, if it cannot do it, then nothing else can. Within the space of algorithms which assign priorities statically. If you allow algorithms to assign priorities dynamically, then there are better algorithms. But within the space of statically assigned priorities, if rate monotonic cannot, then nothing else can. So that's a good, interesting sort of result. And back in, and this actually goes all the way back to 1970s, when kind of rate monotonic algorithm was theoretically kind of came out by faculty at Urbana-Champaign. And the very famous result is the following. They basically showed that if processor utilization, given a set of n tasks, if their processor utilization is less than equal to this number, n times 2 to the power 1 over n minus 1, then that set of n tasks, independent of what their C's and T's may be, will always be schedulable using rate monotonic. Okay, so you give me n tasks, I check against this limit, and if the processor utilization is less than this, then we know that rate monotonic can schedule, namely it can run with our policy of highest priority always running, and all the deadlines will be met. Now for n equal to 2, this means it's 2 times 2 to the power 1/2 minus 1, and kind of you work the numbers out. I think it's like 0.8384, something like that. Okay, for n equal to 3, it's 0.78, something like that. And actually, as n goes to infinity, it asymptotes out to 0.69. Okay, yeah, in terms of exponentials, so whatever, 1 over e or something like that, or e to the power minus 1. So it asymptotes out. It basically means that if I give you a task set with an arbitrarily large number of tasks, if it is below this 0.69 threshold, then that task is always, that task set is going to be schedulable. So any task set whose processor utilization is less than this magical number of 0.69 or so is always guaranteed schedulable using rate monotonic. Okay? Now, it's not a very, if you think about it, it's a pretty slack result, because it's basically saying that if you're willing to give roughly 30% of the CPU, which is roughly, 30 over 70, so like roughly 40% faster than what really I need, potentially, I can always guarantee scheduling. Okay, but could we do better? Kind of remains a question. So this was kind of the theoretical result from that size. Now, what it also says is that if I have a task set, let's say for n equal to 2, n equal to 2 is around 0.84. So let's say I give you a set of 2 tasks. We know if it is utilization is less than 0.84, that set of 2 tasks will be schedulable. But if it is more than 0.84, what does it mean? Can still be schedulable, because this condition is sufficient but not necessary. Okay. In fact, there may be tasks all the way up to utilization equal to 1 that may be schedulable. It's just that this particular rule is not detecting it. They may still be RM schedulable. They may still be schedulable with some other static priority assignment also. It's just that this rule is not powerful enough to catch it. Okay, so what happens now if my task set happens to lie out here? How can I detect that? So this is giving us kind of a bound, but it's not, doesn't appear to be very tight bound. So could I do better about this? So that brings kind of another notion, something called the critical instant of a task. So a critical instant of a task is kind of an attempt to define that if I'm checking, remember earlier on I was drawing those timing diagrams, and I kind of basically said, oh, let's assume that those 2 tasks came at the same time. But why the same time? Why not staggered? Which is the worst case? Is the worst case for a task when it comes together with other tasks? Is the worst case when it arrives staggered? Well, critical instant theorem says that a critical instant for a task, which we define as that situation where it will have the worst case response time. Okay, that is, it will take the longest to finish. So critical instant for a task occurs whenever the task is requested, that is, a job of this task comes simultaneously with request of all higher priority tasks. So if I'm doing rate monotonic, let's say, so I have assigned priorities according to rate monotonic. Let's say I'm looking at the task which has a 3rd highest priority. And to analyze the behavior of this task, what this theorem is saying is, analyze the behavior when a copy of this task comes together with a copy each of the 2 higher priority tasks. And by the way, this strategy will work for any static priority assignment. Okay, for sure for rate monotonic, but if you try out some other priority assignment, same thing. So what this is saying is that if I can prove that a task does not miss its deadline when it comes at its critical instant, then I have proved, and I show it for every task in my system, then I have showed schedulability. So a strategy for showing a system is schedulable for a given assignment of priorities is, I take the highest priority task, check whether for highest priority, since there is nothing else, so all I need to check is that C should be less than T, okay, which is obvious. Then I go to the next highest priority task, whatever it is according to my rule, and I say, let's assume this task arrives at the same time as a copy of the highest priority task. And now I simulate the system. Okay, simulation means that I have to take into account multiple copies of the multiple instances of the task arriving later on. I simulate the system and I see whether this copy of task which came at t equal to 0, did it finish in a timely fashion? If my simulation shows that, I'm done with task 2. And I move on to task 3, and so on and so forth. And you have to check for every task. That is, if I have 1,000 tasks in my system, you cannot simply say, oh, let me check the lowest priority task and see if it is schedulable. Because ironically, it may turn out that it is schedulable, but something in the middle is not. So you actually do have to check everything one by one. So this obviously is a more powerful rule because firstly, it is not dependent upon rate monotonic. I can apply this thing for any priority assignment. So you give me a task set and you say, hey, I'm thinking of putting these static priorities. Will it work? I can apply this strategy. I can also apply this strategy if I did rate monotonic but found that my task set was outhit. Then I could also apply that. Question?
Excuse me, this rule will apply for primitive systems.
Right. So this rule is all the discussion that we are doing at this stage is for the case preemptive, static priority assignment, and deadline equal to period. Okay, all the three conditions are met. So, example, task 1, task 2, I have period of 2 and 5 and computation time of 1 each. We start with task 1 having the higher priority than task 2. So this is what happens. So I basically say, I look at copy of each one of the two tasks arriving at t equal to 0. So firstly, task 1, we can easily see that it needs 1 unit every 2 time units, so it trivially meets its deadlines. Okay, each instance will meet its deadline. Task 2 is the more important one. So task 2 is coming every 5 time units, t2 equal to 5, but it needs only 1 unit of computation time. And in this case, you can see that critical instant of task 2 is when it came at the same time that a copy of task 1 came. So task 1 gets a priority. So at t equal to 1, it starts running and it gets this 1 unit of time. So deadline met. What if I were to increase computation time of task 2 from C2 equal to 1 to C2 equal to 2? There are many reasons it could happen. It could be that I decided to change task 2. It has a costlier algorithm. It could be that when task 2 is running, I decided to save some energy, and therefore I'll run the CPU at half the frequency. Okay, any number of reasons. And if that's the case, so I'm running CPU at half the frequency during task 2 only. Task 1 is still running at full speed. I can still meet the deadline, as you can see. What if C2 is more than 2? Can I meet the deadline? No, because I have no slack left at this stage. So so this is called critical time analysis, and critical time zone basically is kind of from the point I came to the point I have to finish things. Now consider the other situation. Task 2 has the higher priority. Task 1 has a lower priority, so first I check task 2, came at t equal to 0, needs 1 unit of time, finishes much before its deadline, I'm done. Task 1, it gets a lower priority, so it starts running at task t equal to 1, even though it arrived at t equal to 0, and it finishes at time 2, I'm done. Now in this system, can I slow the processor down for either of the tasks? No, because if I slow processor down for task 2 or make task 2 even a teeny bit longer, task 1 will miss its deadline. Okay, so you could see same processor, same CPU utilization, but different scheduling strategies are resulting in one case slack, in the other case no slack. So here I can potentially save some energy while I'm running task 2. Okay, by running it slower whenever I'm running task 2. Here I have no possibility of doing that. So the way you assign priorities matters. It can make otherwise schedulable system non-schedulable. It may let you get away with a cheaper, lower power, whatever, safe power. And finally, the way you analyze these things, I mean, in this simple example, maybe I could have even done the analysis using the alternative approach, the formula. So let's see. In this case, 0.5 plus 1 over 5. So my total processor utilization is 0.7, which is less than 0.84. So simply by my rate monotonic rule, it was schedulable because its utilization is 0.7. The threshold was 0.84, something like that for n equal to 2. So this was schedulable. So even my other analysis would have shown that this is schedulable. But this approach is giving me more insight. For example, what if I had told you that, task 2 is really critical. I do want it to have the higher priority. Then the rule would not have helped because that is task 2 having the higher priority is not a rate monotonic assignment, and therefore I could not apply this rule. Okay, and therefore this kind of analysis would be my only approach. And what I'm really doing in this analysis is I'm actually simulating the system. Okay, I have to simulate the system for every task, and I have to simulate it for a bunch of cycles. Okay, so it's obviously a more complicated way of checking schedulability than just evaluating that formula, but it gives me, sorry, but it gives me more insight. I can do more stuff into it. Um, so limitations of this thing. As we can see, a limitation of from just the example I just presented, a limitation is that it's not always possible to fully utilize the CPU. So in this particular case, even though the CPU is only 70% busy, but I cannot slow. I have just no way of exceeding that. If I increase C2 or C1 even slightly in this configuration, the system becomes non-schedulable for that particular priority assignment. So fixed priority assignment is not good in the sense that it forcibly keeps the CPU idle just so that we can meet the deadline. Okay, in some case. So even though uh, 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 so even though rate monotonic is kind of nice optimum in the sense that if it doesn't work, nothing else will work among static priority assignments. The problem though is that the only promise in a strict sense it is making, that is across all task sets, across the universe of task sets, the only guarantee it is making is that as long as my processor utilization is less than ln2 0.69, I'm okay. Anything above that depends. Okay, so it has some slack. Again, from the first example I was doing, it's possible that a task may have only a 70% CPU utilization, but I cannot slow the CPU down even a tiny bit. I have 30% reserve. It's almost like a car where I have a more powerful engine just to accelerate. Okay, in this case, just to meet the deadline, but I'm actually not using it in kind of for my routine performance. So to summarize this thing, then to check fixed priority schedulability, there are two cases. Then you are not given a priority assignment, or you're given a priority assignment which is rate monotonic. So I give you a task set, and I give you I either say, hey, I don't have a priority assignment, figure it out, or I give you one and it happens to be rate monotonic. So what you'll do is you'll first check against this rule. If this is met, you know it is schedulable. Okay, using rate monotonic. If it is not, if this rule is violated, then you have to do the critical instant analysis. On the other hand, if you are given a priority assignment that is not rate monotonic, okay, then you cannot apply this rule. This rule is for rate monotonic only, but you can still do the critical instant analysis. So then the more general tool we have at our disposal is how can we do the critical instant analysis. Let's look at another example. So let's say I have these two tasks. First one has a period of 100, second one has a period of 145. Their computation times are 20 and 30. Is this task set schedulable? I do a processor utilization. I get 0.828, which is less than, I get 0.41, which is less than the formula, what the formula tells me for n equal to 2, and therefore it is schedulable. Let's say I add a third task to this mix. So this third task comes every time 150, and C3 is equal to 0.68. I calculate U, I get 0.86, whereas for n equal to 3, the threshold is 0.779. 9. So looking at this, I don't know. It may be schedulable, it may not be schedulable. So then I need to apply the critical instant thing. Now, we already knew that C1 and C2 are schedulable together. C3, according to rate monotonic, has the lowest priority because it has the longest period. So in this case, all I need to do is to do a critical instant analysis for task 3, and that is sufficient. So, so now let's imagine, let's look at critical instant for task 3. So the critical instant of task 3 is it arrives, and at the same time, a copy of task 1 and task 2 also arrive. So those copies are going to get the higher priority, and therefore I must budget before task 3 can finish. I have to make sure a copy of task 1 and task 2 also run. So we know at the very least task 3 cannot finish before C1 plus C2 plus C3, because I have to run a copy of task 1, I have to run a copy of task 2, and I have to run task 3 itself. You add it up, it's 118. Okay, so 20 plus 30 plus 68, 118. Now the problem with 118 is that another copy of task 1 comes at t equal to 100. Right? So we have a little bit of a iterative situation out here. So this cannot be my deadline because I have to now budget for a second copy of task 1. And since task 1 is higher priority, it will get that in its entirety. So what that means is task 3 response time has to be at least 2C1 plus C2 plus C3. Add it up, it's 138, and 138, well, by that time, no more copies of task 1, no more copies of task 2, no more copies of task 3, we are done, so my dead response time is 138, and it's less than 150, so I'm good to go, okay? Now, this is obviously kind of analysis done kind of in this verbal fashion. You can translate that into a program or into a set of equations to kind of do the same kind of analysis. So that's the way schedulability is tested. Now, how things play out in the OS would be the following. Up front, your program would basically first declare the set of threads it has. For each thread, it will specify T and C, and it will ask and the OS will go through what is called the schedulability analysis, and it will say, okay, will the deadlines be met or not? So you ensure that, and then you basically would issue something like run, okay? And then from that point on, after that point on, if you decide to add a new task, you have to do the whole schedulability analysis again. You cannot just decide to run. You cannot just decide to change T and C. So there's a contract you have to create with the OS where you say, I have these many tasks, these are their timing properties, the OS will accept them, and that's what it's going to insist upon. Now, these kind of operating systems are going to have or may have mechanisms where if you violate C, they are going to kill the task. So if there is a job instance which starts exceeding its corresponding C, it will be stopped. Okay, either that or maybe some emergency handler will be called or something like that. Okay, so there are many different ways kind of things can be handled there. So that's the way to kind of analyze this thing. Now, in recent years, just a few years ago actually, the group in Italy showed that there is another formula which actually is tighter. What it does is, so going back out here, remember this one corresponded to this one. They showed that there is another formula which results in a curve which is much higher up, and it catches, just through a simple formula, it catches more of the cases. And that is attractive because this test, a formula like this, is a lot computationally a lot easier to do than kind of doing this kind of than kind of running through this kind of a simulation. Okay, because this has complexity which corresponds to a bunch of firstly it's at least number of tasks. Okay, so it's O(n) at least, and then it's also actually in terms of how many cycles have you taken, and actually in general it may boil down to LCM of all the periods. That's your worst case kind of a situation, kind of a hyper cycle of some sort. So the search for coming up with a better formula has always been on, and what this group showed was that there is a better formula which, if instead of simply knowing the total processor utilization, if I actually knew individual processor utilization for each one of the tasks. So the previous formula said U is less than equal to N, blah, blah, blah. It only needed to know U, which is the sum of all the individual tasks utilization. If I knew, instead of the sum, if I knew individual tasks utilization, then what this group showed is that this formula, it basically says 1 plus U sub I, and I take the product of it across all the tasks. If it is less than equal to 2, then the task set is schedulable by rate monotonic. And what they also said was that this is the best formula you can come up with if all you know are the UIs. I don't know if I don't know the if I that I don't know individual CI. I don't want to bother with individual CIs and TIs. I just want to deal with process utilization. And this is the optimal formula. There's nothing else that you can do. But this bound is actually much better. This curve lies much higher up. So now we revise our strategy. If I'm giving you a task set where either rate priority is already given to be rate monotonic, or no priority is given, so you're going to make it rate monotonic because we know rate monotonic is the best you could do, then you are going to apply this formula. If this results in less than equal to 2, you know it is schedulable. If it is not, then you go back to the critical instant analysis. So in the worst case, you cannot escape critical instant analysis, but since that's a much costlier test, you first try to apply the formula. So same complexity in the sense the formula is a straightforward formula, but significant gain over the classical test out there. So let's take a few minutes break, and then I'm going to show how we can do response time analysis in form of a program. Okay. So 5-minute break. If any of you have any questions about the project, come and talk to me.
I think there's a typo error on the slide 18.
18? Oh, yeah. Okay. Thanks for pointing out.
So what I was thinking is that there are now multiple sensor systems. So there is one sensor system which is where the company is the data and things. So then there is another sensor system which is since the different physical thing. I know that people. So at the end of the day, when there are so many sensors and so many gateways, and then they all so is it not possible that you can create the gateways themselves pretty much can handle almost any of the three sensor systems? So can't they use something like a hypervisor for isolating all of these three so that the data is maintained for all of these companies and is secure and can only be accessed by those persons who are ready for that, and then we can definitely pull it in.
Yeah, I guess probably the only thing really out here would be the file for you, which is the part of the reason they have these gateways, separate gateways, is that they also have different radios, right? I mean, okay, so that's one issue. The other issue is that if you were, let's imagine you're a company, you came up with this idea. How would you convince these different sensor vendors to put their stuff in a hypervisor in a form? Now, and going further, actually, if let's say they were to open up things, then instead of doing the hypervisor way approach, I mean now in Linux you have this ability of containers, right? You would probably like to use that, right? I mean, we are not like
security that is provided by using hypervisor mechanism is much different because hardware is now supporting hypervisor extensions which provide much more enhanced hardware level security. So compared to container hypervisor approach will be much better because processors now support hypervisor extensions which provide hardware security. So that is much better isolation and much more secure. So every company is assured that okay, their data is only accessible by their system because each operating system will be maintained well. They can obviously lock it and access. Just what can happen is one sensor is connected to Bluetooth, and then we connect over wire, and then we connect over some other technology.
Yeah, I mean, it sounds like an interesting thing. I mean, I think to flesh it out a little bit, but I can see the case you're making. You're right. I mean, each one of them is a embedded Linux box. Okay, doing essentially the same thing, and you end up with too many of these things, and there's fundamentally no particular reason do it. Now, of course, there is, like I said, the radio issue is still there because a lot of times they kind of basically want to have their own well-defined network and not kind of have to deal with this issue. But could I still so think in terms of some concrete example. What would that be? And arguably at some level you could say that in in a non-home like in a smartphone context that is already happening, right? I mean, there are a lot of sensors which use our smartphone as gateways, except that in this case they kind of install apps to kind of right. So there obviously they are relying on the sandboxing provided by the app framework. So in kind of the home gateway setting, could the same thing be done? Now, another way of possibly formulating the problem is, why don't my home gateways look like my iPhone or my Android device, right? I mean, and then let these companies kind of write apps in there, okay? So if let's say one were to have a situation like that, what would it kind of look like? So I had a student who had started on a concept and all, and it didn't uh, go too far along because I think he's a little bit lost in the architectural side. But let's say you reframe your thing. So let's say I were to give you, you have a box which is running Android. People both can run Android actually. And now you were to provide a framework where essentially for a building or a car or whatever, you have this system where companies can come and write a device gateway kind of thing where gateway takes the form of first, okay? And what Android could do is, in this case, provide common access to external sensors. Okay, so currently in Android you have a sensor API defined for the built-in sensors, and of course you have Bluetooth. Okay, but when it comes to Bluetooth, it's kind of the open world and all. Could we provide and for why? Usually there isn't much of a Wi-Fi type sensor access, but you can imagine also that. So you could imagine there is an app sitting there, but you can call it a gateway server. What it does is it kind of talks to sensors and it exposes these sensors in a common framework with the apps. Okay, let them discover it and all. Now, it is a little bit like this, and maybe that could be the direction you could take. There is this thing called all join, which is discovery and kind of slash talking to sensor kind of a framework that bunch of companies started this project at Qualcomm, kind of did, and they have clients for all sort of devices like smartphones and even tiny devices and all, and then they have discovery protocols and there's common way of talking to these things and all. So I would be pretty keen on doing a project around that. But all that would take is the following: that maybe evaluate how. So the way it would be the following: that you already have your phone, you have your embed device, your phones and all. They already have pieces of code and all. Create an all-join type framework and do some evaluation on it. Okay, and your goal would be that you create this concept. You're saying that I have a device which is a gateway device or a home thing, so that uses all join because it's kind of emerging industry standard, and provide this kind of ability where I can write new apps which speak to the existing set of sensors. So, like for example, I deploy sensors. Currently, one thing you didn't state is that I buy the sensor and the gateway as a single package, which is kind of and the associated cloud service. Really, the two can be decoupled. If I don't need n temperature sensors from different companies, all of them, okay, I should have a temperature sensor, and then it says, hey, I'm a temperature sensor. And if one company is providing me a fire protection service, it uses it. Another company is providing me, I don't know, comfort service, it uses that. Okay, so all join would enable you to do something like that. So maybe what you could do is kind of using all join, kind of create this framework where all sensors in my home are visible in this common framework that AllGen provides, and then this notion that I can have apps running on top of it which talk to their own cloud services. Okay, so that would be kind of a, and instead of reinventing the wheel, use all join because they already it's open source. Things are out there. Use BeagleBone as as the gateway platform, and then your clients could be maybe you can pick a Wi-Fi sensor, you have Bluetooth sensor, and perhaps your phone and another sensor. Okay, and they all kind of talk to this thing and kind of provide.
So I mean, is it a feasible project?
Yeah,
Under timelines? Because I'm not
it should be. I
really
mean,
good
so,
at stuff.
so it depends upon how good you are with software.
Yeah, okay.
What's your background?
I mean, I'm not Android application as such, so I'm not weak on that, but most of the stuff I
You know Java? I mean, Android is not that hard to pick up in a way, and we are doing a class on that, so you can always hit upon my students and all. All join, from what I understand, is a fairly robust framework, and also you're really doing kind of stuff on top of it. So it's not like you're doing any systems programming and all. I think the part which you will have to kind of do is that. Pick a couple of sensors, one sitting on the Wi-Fi network on which your BeagleBone, and you'll have to kind of hook BeagleBone. Sorry, Raspberry Pi. Yeah. So hook up Raspberry Pi with a Wi-Fi and perhaps a Bluetooth, and kind of have two sensors, and provide this ability that app can discover either one of them. That all joint should provide. So I think should be doable, and if someone is still looking for a team partner, you can always. It should be an interesting project. It will expose you to kind of a new emerging technology. It's a standard which so many companies have bought into. So, thank you. Sure. Hi.
I don't know if you have time right now, but I just quickly, for I squared C, I know you can, yes, you can attach multiple devices. If one's operating on 3.3 and others on 5, they all have to be the same. Well, the embed, I think, is it's when you're using I squared C, it's kind of sharing the accelerometer and the external one's probably sharing that same port. I don't know if there's a dedicated I squared C just for the external ports. I think it's shared among the devices that are there.
The first thing my suspicion is that usually the I2C pin is probably the same pin. Oh, okay. But I think I2C standard would be
Yeah.
what is the word?
I think it was the range.
Yeah, it was flexible. It handles a number of different including frequency.
But it uses like a pull-up, 10K pull-up resistor, and I was wondering that maybe if you had a device operating at 5 and then 3.3, the voltage, the current will just be burned in the resistor, and therefore you can actually have two devices operating. I believe the embed is 3.3.
On the embed, it said there was 5 capacitors including the battery. The 3.3.
Yeah, there is.
All marketing my students is pretty good upon
The reason we're trying to determine this is we're looking at infrared sensors to send you to so I don't want my sensor.
also, you are the one who every day comes so I need to order the grid for you.
And then every time you're
Okay, so when we get
Yeah, if you need a score, you can. I mean, my students know. Yeah. Huh? Oh, I must have called. So you need USR. Okay. So. Okay. So you want to use USRP. Okay. You go to the lab and okay. He has the USRPs. Although I was talking with him, and he was suggesting that 5300 may be the better way to go. It seems a lot easier. In the Intel board. It seems like it's a lot easier to use solution. No, we'll have to buy it. We'll have to buy it. You swing by and talk to Paul in person.
Yeah, we have to see him today.
Okay.
I just emailed him.
Okay. Yeah. USRPs we have, so you can always take it from him. 5300 we'll have to order. Okay. Okay, let's restart. Sorry. So, I want to talk about like how you can do this response time analysis. So, response time analysis, the nice thing is that it actually gives you a necessary and sufficient condition, unlike those formula which were sufficient but not necessary. So, so the way to kind of think about it is, so we are not going to end up with a formula out here because recall the whole process is kind of a little bit of an iterative analysis, and we're trying to show that okay, that deadline is met. So we are going to come up with an algorithm which mimics the process of doing that simulation. So for the so imagine now that so I have a set of tasks, I have assigned priorities to them. It may be rate monotonic, or it may be some other static priority assignment that I will be given. So I can say that tasks are sorted by some priority ordering. If I look at the highest priority task, its response time is going to be its computation time. Needless to say, right? I mean, whenever it comes, it will take that much time to finish. Now let's look at a lower priority task, some lower priority task. The response time of this lower priority task is going to be its computation time, Ci, plus whatever interference it sees from higher priority tasks. Because whenever a higher priority task issues a job, it will get the CPU and this guy will have to wait. So there will be some interference. And also critical instant theorem tells us that the worst case response time would be when this task, ith task, arrives at the same time as a copy of each one of the higher priority tasks. Okay, so let's imagine that we call, for the sake of argument, let's imagine that we consider that the set of tasks which are higher priority than task number I is, we call it as a set HP of I. So HP of I is the set of tasks whose priorities are higher than the priority of task I. And we are trying to find the response time of the ith task. So Ri equal to Ci plus Ii, which is coming as a result of the tasks in HP of I running. So could I come up with a formula for HP of I? Well, let's consider some task J, which is a higher priority task. Then, and let's try to see what interference it will present to us. Well, remember, we assume that the response time of ith task is R sub I. During that R sub I, there would be ceiling of Ri over Tj, that many jobs of jth task arriving, right? There will one at the very beginning, and there will be a few subsequently. So there, you convince yourself that this would be a ceiling function as a result. Okay, so that many copies of jth task need to be run. Of course, we have a recursive problem because I'm expressing this thing in terms of R sub I. And these tasks are going to need time equal to, again, ceiling of Ri over Tj multiplied by Cj, because each instance of jth task needs Cj time. And then I can sum it over all the higher priority tasks. So this formula at the bottom gives me the interference that the ith task is going to see from all the higher priority tasks, and it's basically saying sum this term Ri over Tj ceiling times Cj across all the high priority tasks. Okay, so any questions on this? So it's just algebraically kind of expressing kind of a notion that I have to handle each one of those high priority tasks. And that gives me my formula. It says R sub I is equal to C sub I plus the interference. And if I could solve it for R sub I, then I'm done. Now, of course, this ugly ceiling function, and the fact that it's a recursive formula kind of creates problem, but this kind of equation we often face in math, x equal to fx, and I have to solve it. And if I cannot explicitly do it, then we employ numerical techniques, and a very common numerical technique is that we kind of just iterate over this equation and hope it converges. So I'm going to start with some value of x, calculate a new value of x by x equal to fx, and iterate that process. And if I can show that this will converge, I'm done. Okay. Now in our case, if as I iterate, if x exceeds the deadline, that means we can stop. And if it converges, that is at some point we actually find that x is equal to f of the previous x, then also I'm done. So there's a well-defined stopping criterion. Now, the other thing you can see is that given the structure of this, as I iterate, Ri will only increase, right? I mean, because I'm adding Ci, this thing, every term is positive, right? So every time I iterate, Ri is increasing. So at some stage, either Ri will stabilize to constant value, it will reach the fixed point, or alternatively, it will exceed my deadline. So I have a clearly very well-defined stopping situation. So the way we basically do it is we start with some assumption on Ri, we plug this thing in out here, and then we calculate the next value, and we kind of keep iterating until we hit our stopping criteria. What value of initial value can I start up with? Equal to what? Yeah, equal to Ci. So we can basically say Ri equal to Ci. That's a good value. You can even start out with 0 actually. It will work out fine too. But higher the value you start with, the sooner you'll converge. Okay, fewer iterations through this algorithm. So now we obviously have a reasonably clean way of writing a piece of code corresponding to this. So this is in some pseudo code where basically we start out with n equal to 0. We set the initial value of the variable of interest to be C sub I, and we kind of just loop where every time we just compute the new thing, and our stopping criterion is if either we have converged or we exceed the deadline. Okay, so one of the two ways we are going to exit out of this thing. And so given a piece of code like this, you can then play all sort of other games. Like for example, so I give you you give a priority assignment, you work on this thing, you find it schedulable. Then you can say, okay, hey, what if I slow down the processor a bit, save some energy? So you can just try it out by changing all the CIs. So slowing down a processor by a factor alpha means that each one of the C sub I increased by the same factor alpha. Rerun the algorithm, see what happens. Okay. In reality, most task sets are small enough that something like this is not going to take a long time. I mean, a very complicated embedded system may have a small number of tens of tasks. So we are not talking about worrying about n equal to 1,000, 2,000 and all those kind of things. I mean, these are 10, 20, 30 kind of tasks. Those are complicated enough. Those are the kind of stuff you'll find in automobiles and stuff like that. So having a tool like this, particularly if you're just running it upfront, it's perfectly fine. This is kind of a reasonably robust piece of code. You can iterate on it. You can do some branch and bound kind of thing to find the optimal processor speed. You can play all those kind of games out there. There is indeed a way where you could also express these things a little bit more algebraically as opposed to kind of like this kind of a algorithm with a loopy structure. And the way it works is the following. Okay, I'm going to just jump to this thing. Okay, so let's no, I don't think I can jump. Okay, so same situation. I have n tasks, and they have been given some priority, and I can sort them without any loss of generality. I can sort them in a decreasing order of priority. So task 1 is highest priority, task 2 is the next one, and task n is the lowest priority. So for task I to be schedulable, a necessary and sufficient condition is that I can find some time t, such that t is greater than how much work is needed during that time. And that work consists of Ci running and the necessary copies of each one of the higher priority tasks running, right? If I'm able to find some t which has this property, that would be sufficient. That's sufficient and necessary. If we don't, then it's not. Now looking at this, you can also see in this equation, let's say I start out with t equal to 0. And as I increase t, checking for this criterion, then the only time the right-hand side will change is whenever the ceiling functions change their value. And these ceiling functions change their value only at multiples of t1, t2 through ti minus 1, right? So as I'm increasing t, it's not as if this right-hand side is increasing in a smooth fashion. It jumps at multiples of t1, t2. So another way of saying is, I really need to check existence of this t at values which are multiples of all the periods. In fact, periods, small periods which are smaller than the one for the ith task. So that's the insight that we kind of bring to where we basically say that checking a necessary and sufficient condition for checking for schedulability is that I check this equation for all values of t which are multiples of t1 or multiples of t2 or all the way through multiples of ti minus 1 and are less than t sub I, because that's my deadline. Okay, or are less than the deadline, whatever my deadline, if deadline is less than t sub I. So this, fortunately, now I've suddenly turned into kind of, I can express this thing as a finite number of equations. Any one of them, if it is satisfied, I'm good to go. So I can expand this equation into a search over all multiples of t1 which are less than equal to ti, all multiples of t2 which are less than equal to ti, all multiples of ti minus 1, each one of them is going to give me a different inequality, and any one of them, if it works, I'm good to go, because all I need is a t. So that's kind of the basic idea out here. So we define how much work is needed in time t. The work which is needed in time t is all the copies of different tasks which are arriving. So all the work which is needed in time t, and if I'm considering task I as my test. So this is all the copies of higher priority tasks as well as this guy ith guy itself that are going to arrive. So this is a total work that is needed in time t. We define this variable li of t as being wi of t less than t. So what schedulability in this case, basically the previous slide ends up saying is the following, that I first want to find the small, for the ith task, I want to find the minimum t which is less than the period of the task, and sorry, I want to find that t which is within this thing which minimizes this guy. Okay, so the minimized part refers to this workload. And remember, our requirement is that work in time t should be less than time t itself. That is, I should have more time available than time needed. So, so in many ways, what we are really looking for is that the smallest value of li should be less than equal to 1. That is, there must exist some t such that li of t is less than equal to 1. Another way of saying is, if I look at the smallest li of t, and let's call it li, then li should be less than equal to 1 for ith task to be schedulable. And then for the task set to be schedulable, I can look at the highest li across all my tasks, and then I'm basically saying that this L should be less than equal to 1, right? So each task should be schedulable. So ith task being schedulable means L sub I should be less than equal to 1, which is, and then for the task set to be schedulable, L should be less than equal to 1. So this is a general and sufficient condition. It's saying task tau I can be scheduled if and only if li is less than equal to 1, or another way of saying is there exists a t between 0 and the period of task I such that the work required during that t was less than t. Okay, and for the whole task set to be schedulable, this last line is saying all tasks should be schedulable. Okay, so I have to basically look at the highest of this guy. So practically speaking, since I don't have to search for all the t's, so the previous slide pointed out, I only need to check it at those values which are multiple of t sub j, where j is between 1 through I. So, so what that basically translates into is a set of inequalities. So let's look at an example. So let's say I have this task set. I think I may have messed up the data on the next slide, but at least it will give you the approach that I'm following. So I have 4 tasks. T1 equal to 100, C1 equal to 20 through this, okay? And let's say I did the rate monotonic assignment in this case. I didn't have to, I could do the same experiment with any priority assignment. So task 1 has the highest priority, task 4 is the lowest. So what I now need to do is I need to come up with the sets of T's at which I'm going to check schedulability of task 1, schedulability of task 2, and so on and so forth. When I'm considering task 1, the values of T at which I'm going to check are multiples of T1. So the only thing I want to check is 100. Okay, multiples of T1 which are less than equal to T1. For task 2, I'm going to check at multiples of T1 and T2 which are less than equal to T2, which is going to be 100 and 150. For task 3, I'm going to check at multiples of T1, T2, and T3 which are less than equal to T3, which is 100, 150, 200, which is a multiple of 200, 100, and then 210, 4 values. And then finally for task 4, I have to check for multiples of T1, T2, T3, T4, which are less than 400, less than equal to 400, so it's 150, 200 multiple, 210, 300 because of this, and then 400. Okay, so those are kind of our values. So what it means is that corresponding to task 1, I have one inequality. And for it to be schedulable, that inequality better be met. For task 2, I have 2 inequalities. And if either one of them is satisfied, I'm good to go. Task 3, I have 4 inequalities. Any one of them is satisfied, I'm good to go. And finally, I have 5 out here. I have 6 out here. Any one of them is satisfied, I'm good to go. And for the task set to be schedulable means that in each group, I should have one inequality which is satisfied. So I could structure it this particular way. I'm not going to walk through this thing, but on the next slide, I kind of showed that what happened. I think I might have messed things up, so you might want to sort of work it out. But the idea is for task 1, I calculate W1 100, which is 20. And so what this is saying is that work needed in time 100 is 20, and therefore I'm good to go. Task 2, I have 2 inequalities. I compute both of them. W2 of 100 is 50, which is net. So work done is needed is 50, time available is 100. And I likewise do it for 150. In fact, I didn't even need to check the next one. I checked one, I could stop. Task 3, I check for 100. I need work of 130, so that doesn't work. If I check for 150, that works, so I'm good to go. All I need to show is one of these is met. Task 4, shown similarly. I may have something wrong, but concept is in each group there should be one green. That is one inequality which is met. By the way, in this particular example, if I were to try out the U test and the 2 tests that we have, so we check it out and we see that the processor utilization is 1.03. So obviously not schedulable. Doesn't make sense, and that obviously we detected, and likewise out here. Okay, so comments on this thing. We have sufficiency test. We have sufficient necessary insufficiency test. Exact tests are costly. They are based upon this critical instant analysis, so you have to kind of go through this process. There are other tests that people have tried to do. The reason this is important is because it happens at runtime. So ideally you want something that the OS can do with very little overhead. A generalization of this, which works fairly easily, is that if I have di less than equal to ti, and obviously di has to be greater than equal to ci. Okay? So if we are in this regime, then all it says is that we compare di's and assign priority in that order. So if di is less than dj, that means priority of I is more than priority of j. And the two, needless to say, may differ. Like for example, I have a task set out here where you see the periods are 20, 15, 10, 20, but the deadlines, for example, you would see that task 2 has a period of 15, but a deadline of 7. So period of 15 would suggest it should get the higher priority, but deadline of 7 suggests that task 1 should get the higher priority. Okay, so for the case where d is not equal to t, you have to give priority according to the deadlines. Okay, and again, there are results which show that this is optimum, and my critical path analysis actually works for this case also. Okay, the only thing is you're stopping condition changes now. Okay, instead of looking for a time less than equal to t sub I, you're going to look for a time less than equal to d sub I. But rest of the machinery still works. So deadline monotonic, rate monotonic are very widely supported, partly because almost every real-time operating system or embedded OS for that matter, they provide in some shape or form a static priority-based preemptive scheduling. Okay, and all you need is so there's no such thing as a rate monotonic OS or a deadline monotonic OS. It's really a policy for these are policies for assigning priorities. The OSs that you will find will say we are static priority preemptive scheduling operating system, and then how you assign the priority is your job. Now, in some operating systems, they may provide you a service where they may provide the checks that we were describing. In most cases, though, that's not the situation. What they expect you to do is to somehow offline figure out that your task set is good, that is, your priorities are good, and then you assign those things. And then you don't mess with that. Okay, almost all OSs are kind of like that, but there are some where there is an API where you can say to the OS, this is my T sub I, this is my C sub I, this is my D sub I, and the OS will say, okay, we accept this task or not. Okay, and then they are kind of doing this kind of analysis. So these algorithms, this code and all that I showed, you'll typically find it in one of two places. Either EDA tools, where you're designing a system, you have written the code and all, they analyze they compute what the C sub I is, and then they say, okay, this is schedulable, and the tool will say, use this priority. Or alternatively, it might be as part of the operating system. So these are two regimes that it gets used. So that was a story as long as the tasks were independent. The problem is tasks are never independent. It would be a rare embedded OS or rare system where you really have a bunch of disjoint and tasks. It's highly, highly unlikely. So tasks interact, and another way of saying is tasks interact is that there are basically two things. They share resources and they send messages to each other. These are the two ways they kind of interact. And in fact, so sending messages basically boil down to that one task may wait for another task to provide some resource before it can proceed. So it violates an assumption that we have made thus far. Thus far, the assumption was if the task is ready to run, then if I were to give it the CPU, it can run to completion. Okay. But now it's no longer the case because it may wait for a message or it may wait for a resource that the other task has. So what happens under this condition? So in this condition now, thus far for a task, I only had to worry about waiting for interference from higher priority task. But now I have a second source of problem. That is, I may hit an instruction and now I need a resource, but that resource has been hogged by some other task. And worse yet, this task may actually be a low priority task, which happened to have received the CPU and entered the part of the code where it took the resource. So now I may have additional waiting time that I have to factor in, and that will affect my ability to meet the deadline. So this issue happens. So in effect, basically, so firstly, this situation is called priority inversion, where what is happening is that some low priority task has something that a high priority task needs and is unable to run. And this notion where a high priority task is unable to run is what we call as priority inversion. And it turns out you can construct scenarios where this high priority task may wait forever or wait for a long, long time. So even though it's high priority, it may have an insanely long response time. So this is where things start coming into problem. And when first research happened into static priority-based scheduling, I mean, this issue wasn't really well understood and all, and there were basically hack approaches where people will say, okay, let's use a faster CPU. Thumb rules like let's use twice as fast a CPU, and this won't happen, kind of thing. But then in 90s, there were some very high-profile failures which were because of this reason, which is the system was designed, engineers felt that it will meet all the deadlines and all. In reality, they missed the deadline and bad things happened. So, go ahead.
Sorry, when you apply this rule to the first rule, when you choose all the highest priority to know the worst case, so it will not work as here maybe a low priority blocks me and
Right, so you have to now introduce some additional terms. So we'll see how to introduce that when we work out the solution. And the other thing is we also have to prevent bad things from happening, because once you have shared resources, you also have the possibility of deadlock. You have something I need, I have something you need, we can't proceed. And that's standard OS problem, and you prevent it. So as part of that solution, once you are introducing shared resources, you also have to have a solution to that also. So our rule has to change. There's no, we can, but point what boils down to is that we need to somehow compute how much a task can block for. And we won't get it to today, but I just want to show that this can create a problem today, and then we'll kind of pick it up on Monday. So let's say I have task 1 and 3, which share a resource. Task 1 is higher priority, task 2 is the lowest priority. And let's say I have a task 2, which is intermediate priority. Okay, and let's imagine, and this intermediate priority task 2 doesn't need any resource. It's not dependent upon the shared resource. So now consider task 3. Task 3 obtains a lock on that shared resource, that semaphore, and it starts using it. So at some point, task 3 was running because none of task 1 or 2 were ready. Task 3 started running and took a lock on the shared resource. Then task 1 arrived. And task 1 arrives, it's a highest priority task, so it begins to run. And at some stage, task 1 needs the resource, except that it doesn't have the resource. Okay, resource actually task 3 has grabbed. So task 1 is blocked. Okay, it has to wait because it needs the resource and the resource is not there, so it has no choice, it blocks. And let's say around at the same time, task 2 becomes ready to run. Now task 2 is higher priority than task 3, so task 2 gets the CPU. And so task 2 runs, and task 3 is still holding the lock and therefore blocking task 1. Now intuitively, what would you do out here? Now, and what can happen now is that task 1 may have to wait for a long time, right? It has to wait for task 2 to finish, and then task 3, and if we are really unlucky, task 2 may arrive again, and so it may take a really long time for task 3 to release the resource. So if you were designing a mechanism to cope with this problem, what would you
If
do?
a task ever gets preempted, it should release its locks.
If a task ever gets...
If a task gets preempted, it should find a way to be able to release its locks.
You can't. Okay, because resources are not designed like that.
if you're writing a CD or DVD, there's like if you have like a lock on critical section of that task, you can't just leave it out because the DVD or will fail. Like burning trips, like you can't.
Yeah. So what could you translate that into? Right. You dynamically change the priority. So what will happen? I mean, so intuitively, what we would like to do is we want to make task 3's priority higher, kind of inherit the priority of task 1 because it's blocking task 1, and task 1 is very high priority. So we really want to run task 3, not task 2. That's kind of the intuition. So you'll see it next time how to kind of make it happen, and also present some of the failures of this thing. But the point is, this problem got understood around 20-25 years after static priority first came into being, and then kind of the theory got developed around this thing and all, and there are protocols supporting it. The problem is they are costly, so not all OSs support it, and so one has to be super careful that whether there are OSs that can certainly change the dynamic priority. Problem is, if not done carefully, it can lead to chaos. So OSs which actually support safe handling of this kind of situation are rarer because it's a trickier to implement thing. So we are going to look at it on Monday. So again, reminder, Wednesday is Android plus machine learning on sensor data. So we're basically going to have a small lecture on the latter topic and most of the lecture on the Android side of things. And unfortunately, I don't think we'll be able to record that lecture given the way it is structured. So no recording for that.